6 lectures about chapter 3. I realize that's a lot. So, but it's a really important part of the curriculum, because I think it really explains a lot of what we're going to be doing next. And what we're going to be doing next is actually looking at chemical bonding. What are the different types, and how can we represent them in different ways, and really understand their strength, how they're formed, and that will lead into how the nature of these bonds will affect the shape of the molecules, because we'll find out later. I mean, the shape is extremely important. It's not just which elements form a molecule, but how are they arranged in space, and that makes a huge difference to what sort of reactions they undergo. So, are there any questions before we get going?
Do we have recitation this afternoon?
Yes. Yeah, I will post it right after this. We're going to be doing bonding, a recitation on bonding.
Okay.
Yeah.
Okay.
Alrighty. Okay, so I'm going to get going unless there's anything else. And remember, always, raise a hand, shout out, and let's finish chapter 3, shall we? Because we've been doing lots and lots of looking at the periodic table and saying, hey, it's periodic. Yes, it is. What does that mean? Well, it means there's certain chemical activities that change as you go across the periodic table and as you go up and down the periodic table. We learned that taking electrons away from an atom is called the ionization energy. And we saw that the ionization energy got greater and greater and greater as you went across the table. As you go across, atoms get larger and larger, and the nucleus gets larger with more protons and pulls on those electrons, and so it doesn't really want to give them away until you get to the end of the periodic table, where you have the fluorines and chlorines, the halogens, desperately want to pull one more electron in. Now we're looking at the opposite. This is electron affinity. So this, instead of stealing and taking an electron away from these atoms, now we're sort of offering it. Would you like this electron? And so it's the energy change when you add an electron to a mole of gaseous atoms or ions. Remember, we measure these energies for atoms in the gas phase. So atoms with a low electron affinity, like, no, don't want that electron, they tend to form cations. That makes sense, right? Because they do not want an electron. An electron does not help them achieve chemical stability. Sodium, potassium, they want to desperately get rid of that one electron that's in its outermost shell. They don't know what to do with another one. That doesn't really help them at all. If they lose that one electron, remember, they then achieve noble gas electron configuration. Very, very cool, very, very stable. Adding them electron to them doesn't really get them much further in terms of chemical stability. But as you go across the periodic table, as I mentioned before, where the ionization energy goes higher and higher, where it's very difficult to pull an electron away, they want that electron. The electron affinity goes up as well. So it's like the ionization energy goes up because it's really, really hard to take an electron away. And the electron affinity also goes up because that means they want to take an electron. So atoms with high electron affinities tend to form, not surprisingly, anions when they become more stable when you add electrons to them. Those would be elements like oxygen and fluorine and chlorine and sulfur, the atoms that pull electrons toward them. And so as you see on the bottom, the trends for electron affinity aren't quite as regular as those for atomic size or ionization energy, because as we go across, remember when we get to the transition metals, they undergo all sorts of weird electron transitions. They can put electrons in a lot of different places. And remember, when we were stacking the subshells up in terms of energy, as we got higher and higher, those energy differences became really, really small. And so it's very easy for electrons to move back and forth, like for instance, between D and F orbitals or S and P orbitals. They can move back and forth very quickly, depending on which orientation stabilizes the atom the most. So the trend for adding an electron isn't quite as even, but the first two groups definitely want to get rid of electrons. They're going to have a very low electron affinity. And the last three groups or so are going to have a very high electron affinity. What do you think the electron affinity of the noble gases will be?
0.
Pretty much. Pretty much. They don't want electrons and they don't want you to take their electrons. So as we'll see, as we go across, now one thing you need to learn about energies, because this will become important when we do thermodynamics and thermochemistry, looking at the energy of chemical reactions. Negative energy means that it goes forward, means that that is more stable. So if something has a negative energy, it means that energy is basically given off and it becomes more stable than it was before. So you can see that even though I did say that like the first group here has a low electron affinity, and they have a lower electron affinity than other groups, there is some affinity. And that's because they have something out, their outermost electron is in the 2s or 3s or 4s or whatever it is, 1, 1, 1. Now, when you add one more electron, that fills that subshell. So there is some stability gained there, but not very much. In fact, you gain much more stability if you lose that electron completely. So there is some stability to be gained, but not nearly as much as losing it entirely. But as we go across the periodic table, you look at fluorine and chlorine and bromine, those become much more stable when you add an electron. They drop in their energies drop because they're much more stable now. And so when we look at energy, we talk about negative energy, like negative joules. That means that it adds stability. Like once energy is given off, what's left is more stable. So we'll think about negative energy as actually being good and positive energy as being difficult. Because if it's a positive energy associated with it, that means that's energy we have to add to get that reaction to happen. Like for instance, neon and argon and krypton, they're all positive. We have to add a lot of energy to get them to accept that electron. They don't want it. But fluorine, chlorine, and bromine, they become more stable when you add an electron. So remember, when we talk about energies, it may seem odd at first, but negative energies mean more stability, and positive energy means less stability. We're taking something that's relatively stable, and we're adding energy to it so it's a little less stable than it was before. So nature basically wants to always decrease in energy to a more stable place. Adding energy makes it less stable and more likely to fall down later. Okay? So let's just look at the relative patterns. Reactive nonmetals, halogens, oxygen, sulfur, nitrogen, have high ionization energies. They don't want you to take their electron away, but they have highly negative electron affinities, meaning they do want another electron. Yes, I'll have another electron. Thank you very much. They attract electrons strongly and tend to form negative ions. Reactive metals, like the superreactive metals, are the first two groups, right? The alkali metals and the alkali earth metals. They're very reactive. They have low ionization energies. Doesn't mean that they're zero or that they're positive, but they're much, much lower than reactive nonmetals are. They tend to lose electrons more easily. And they tend to form positive ions in ionic compounds. And then when you look at the noble gases, they're just super chill. They have very high ionization energies. It's very hard to pull an electron away from a noble gas. And slightly positive electron affinities, meaning you have to force a noble gas to accept an electron. Okay, so is everyone clear on what the difference between a positive and a negative energy is? If it's a negative energy, that means that's going to happen without really having to do much of anything. Like if you have a negative electron affinity, that means if I offer you an electron, you're just going to take it. I don't have to do anything. If it's a positive electron affinity, means I have to force that electron on you. You don't want it, so I have to force with energy to get you to take that electron. So that's not going to happen unless it's forced. Okay, that's the difference between positive and negative energy, and we're going to talk a lot more about that later. So, any questions about that? Yeah.
What if it's close to zero? Like,
if it's close to zero, then that means it has a very low affinity. It's not likely to happen.
okay.
Like if it's a negative, that means it happens spontaneously.
Okay.
Like fluorine goes to fluoride ion spontaneously. You don't have to get it to do that. It will do that all by itself. But if it's zero or slightly positive, that's not going to happen spontaneously. Something's going to have to force that to happen.
Okay.
Yeah.
Could you repeat the difference between negative electron affinity and very low electron affinity?
Oh, sure. So, like, if we went back, let me just go back for a second. So, I sort of mentioned that these first two, these are the more reactive nonmetals here. First two groups are like really, really reactive as far as the metals go. Now, it doesn't mean that they won't take an electron, that they'll never become negative ions. It's possible, and we see it actually. We see it with hydrogen fairly regularly. Hydrogen will form what's the hydride ion relatively easily, but they even more stable if they lose that electron completely. So if you compared that to their ionization energy, their ionization energy is even more negative for losing this electron. So these are the energies associated with adding an electron. So they'll take an electron if they have to, but if you were to look at the amount of energy that's lost when they become even more stable when they lose it. And so basically if the sodium is given a choice between losing an electron or gaining an electron, it'll become much more stable if it loses an electron. And so that's what's going to happen because it becomes more stable. And so it's very rarely that you'll get the sodium atom to accept an electron, because then when it accepts it, if it loses both those two electrons, it becomes more stable. So basically, you can get it to happen, but then it'll go away. On the other hand, if you look at the halogens, they have they're very high electron affinity. High affinity means that the energy associated with them is highly negative, meaning it will happen spontaneously. This means that when fluorine becomes fluoride ion, it also releases 328 kilojoules of energy. So that's the amount of energy that's given off. So basically what this means is that fluoride ion is this much more stable than fluorine. So the bigger this number is in the negative means that its anion is that much more stable. And so a fluoride ion is much more stable than fluorine. And a fluoride ion is much more stable than a hydride ion is. So the more negative it is, the more stable it is, okay? Does that make sense? Does that answer your question?
Yes, thank you.
Okay, cool. Excelente. All right. So these are some of the trends we've been looking at so far. So remember from the lab some of us did, we were looking at the trends in atomic size. As we go down a group, it makes sense that every time we go down a group, remember we add a shell. So we go 1, 2, 3, 4, 5, 6. It just keeps getting bigger and bigger and bigger. All right, that makes sense. What sort of didn't make sense at first is that when we go this way across the periodic table, those atoms are getting bigger, right? I mean, they're getting heavier at least, but they're not getting bigger, huh? Because the pull on those electrons becomes more and more and more as we add more and more protons. And so actually the shell stays the same, like shell 2, shell 3, shell 4. Those electrons stay relatively the same distance from the nucleus, but the nucleus gets bigger. And so it starts pulling on those electrons more and more and more. And so it gets smaller and smaller and smaller until we add another shell, and then boom, goes up again. Ionization energy has the sort of opposite. The ionization energy increases as you get smaller. So basically, you get much more stability, or the amount of energy associated with forcing to pull an electron away grows as you get smaller. It becomes much easier to ionize as you get bigger, and then also increases as you go across. It takes more energy to pull an electron away as the nucleus is pulling on those electrons. So basically, the smaller an atom is, the harder it is to pull that one electron away. And we'll see that this is related to yet another property in the next chapter. And then with electron affinity, as we go across, things tend to become more and more negatively charged. As we've seen, as we go across, we get like oxygen -2, and nitrogen -3, and fluorine negative. As we go, we have metals on the left side tend to become cations, and we have nonmetals on the right side tend to become anions. So those are some of the trends we've seen as we looked at the periodic table. So when we look at metals, and we're going to look at metals and nonmetals when we talk about what kind of bonds they form. What do we say metals are? Well, I mean, when you think of a metal, you think of something like iron or something, or copper or something like that. They're typically shiny solids, and they have relatively high melting points. Some of them melt at low, like mercury melts at below 0, but most have a fairly high melting point. They're good conductors of heat, right? I mean, they conduct heat through wires, and they conduct electricity rather well, and you can shape them. You can pull them into wires and that sort of thing. They tend to lose electrons, right? They tend to form, whoops, let me go back. They tend to form cations. When we look at, so, potassium becomes potassium ion. Calcium becomes calcium ion. They're oxidized, and we're going to talk about this more in future chapters as well. We talk about oxidation and reduction. Oxidized means it loses electrons, usually to oxygen. That's why it's called oxidized. So when calcium becomes calcium ion, we say it's been oxidized because it's lost these 2 electrons. So calcium went from having no charge to having a positive charge. We say it's been oxidized. So metals are generally reducing agents. Now, what's a reducing agent? Well, reduction is the opposite. Reduction is the opposite reaction. It's when you take calcium 2 plus and you add electrons to it and it becomes calcium again. That's a reduction. So what happens in the presence of a metal? Well, when a metal's given electrons away, somebody else is going to be taking them, like oxygen. Oxygen will go from O2 to O2, to O2, and with plus 4 electrons. So it's going to take 4 electrons. One molecule of oxygen will take 4 electrons from somebody and become reduced. It's basically its charge is reduced. It's gone from 0 to -2. And that will happen in the presence of metals. So generally metals, since they're given electrons away, they will become oxidized and they will reduce other elements around them. So we're going to talk more about oxidation and reduction in the next chapter as well. So don't worry if you don't get it already. So metallic properties also trend. It's also periodic. So, and when we mean metallic properties, basically we're talking about how much they oxidize. Do they oxidize readily? Do they give away those electrons readily? We consider that to be a real metallic property. It's giving away electrons and becoming cations. And that increases as you go this way. Well, that makes sense because we have these are metals. So non-metals become more metallic-y as you go to the left. But what also is true, as they get bigger, they become more metallic in nature too. Because, as we've learned, as the atom gets bigger and bigger and bigger, those electrons on the very outside, on the furthest part away from the furthest shell, away from the nucleus, the valence electrons, as they get further and further away, they're held onto less and less tightly by the nucleus because they're far, right? When we learned that the two things that determine how much pull between charges is how big are the charges and how far away they are. So if they get further away, they get weaker. And so as these elements get bigger and bigger and bigger, those pull on the valence electrons becomes less and less and less. And so they ionize even more easily. So sodium is small, but rubidium is big. And so rubidium is even more metallic in nature than sodium is. And so if you throw rubidium into water, you get an even bigger boom than when you throw sodium in, because it's even more metallic. Its ionization energy is even smaller. It's really easy to get rid of that electron. And so we say its metallic property is greater because it's easier for it to become a cation. So on the test, we looked at electron configurations, and we sort of learned a little bit ago in the last chapter about noble gas electron configurations. And I keep saying that the magic number is 8. It's usually 8. Everybody wants to get to 8, pretty much everyone. The really, really small elements, hydrogen, helium, boron, beryllium, basically want to get to looking like helium with only 2 electrons. But everybody else wants to look like a bigger or a slightly smaller noble gas with 8 electrons in its outermost shell. And when they get to do that, then we say, remember, they have a noble gas electron configuration. And we say that it's isoelectronic. Isoelectronic means what? If 2 things are isoelectronic, what does that mean?
Iso means same.
Mm-hmm.
Electronic means electronic. The same
Electronic does indeed mean electronic, yes. But what does that mean?
The same electron configurations of noble gases.
Not just that, it just means that it's the same number of electrons. Like that's real simply, it just means the same number of electrons. So sodium ion, it means both. But the more simple explanation is that if you just look at the numbers, sodium has 11 electrons. Sodium ion has 10. So it has the same number as neon does. And if it has the same number of electrons, it also has the same electron configuration. So sodium loses an electron to get to look like neon. Bromine adds an electron. Bromine has 17 electrons. It adds one more. And now it's filled that last p orbital. And now it has, oh, that's not 17. That's something, that's 35. Sorry. Now it looks like krypton. So it's added an electron to get to look like a noble gas, whereas sodium lost an electron to get to look like noble gas. Why? Because sodium is a metal. Sodium is more stable as a cation. Bromine is a halogen in the 7th group. Bromide ion is more stable than bromine. So each one of them achieve more stability by becoming an ion, but different charges. One, the metal loses an electron, the non-metal gains an electron, okay? And that's sort of summed up here, looking at the first two groups and the last two groups. And basically, they all want to get to the same place. And they all want to get to looking like a noble gas. So the metals, this is a little confusing, is that the metals on the right side and the non-metals on the left side. It really should be the other way around because the metals are obviously on the left side of the periodic table. But the point that's being made here is that the non-metals add either 2 electrons or 1 electron to achieve the number of electrons of the noble gas in that same row, in that same period. Whereas metals, on the other hand, give electrons away, either lose 1 electron or lose 2 electrons to go back and look like the noble gas in their period. So oxygen, sulfur, selenium all become -2 ions, whereas magnesium, calcium, strontium, barium all become +2 ions. But they're all going to the same place. They're all going to look like, they're all trying to achieve that noble gas configuration. That's basically what everyone wants to do, because that is the lowest energy and so most stable conformation of electrons you can have. They're just going about it in different ways, because these elements, the nonmetals, have high electron affinity, and these metals on the other side have low electron affinity. Okay? Is that clear to everybody? I think we sort of talked about this in previous classes. Basically, everyone just wants to get to chemical nirvana, and what chemical nirvana is a noble gas electron configuration. That's all everybody wants. So you can also achieve what we call a pseudo noble gas configuration. Whoops, let me go back. What's a, oh. There we go. You can also achieve what's called a pseudo noble gas configuration. I mean, it's almost a noble gas configuration when you empty completely the highest energy level. So these are what transition metals basically do. Some transition metals. They achieve the stability by just dumping all the S and P subshells, just dumping all their electrons out, leaving a filled D subshell in the shell below. So for instance, if its 5th shell is filled and the 6th shell has electrons in the S and the P, it'll just dump all of those, leaving you with a filled subshell, a filled shell below it. Like for instance, here's tin. So tin has 4 electrons in its outermost shell, 2 in 5s and 2 in 5p. And so it will achieve stability in this regard, by dumping everything in the outermost shell. It'll get rid of all of them. And so it will look like krypton, but with a full with a full set of d electrons as well. So krypton basically has a completely filled outer shell. But since d is such a high energy orbital, if you can get it completely filled, you get a substantial savings in energy by doing that. So if you can fill a d subshell to completion, you do that, and you get rewarded with a big drop in energy. It becomes much more stable. So this sort of looks like krypton, but not really, because basically you have your outermost electron shell is now empty, but you don't exactly look like a noble gas. Pretty close to a noble gas, but not really. So the other thing that tin can do is just lose the p's. So just dump those p's. That way you have a full s subshell. So you have a full s and a full d, and this way you've only lost 2 electrons. So instead of having tin 4, you have tin 2. And that's how you get different charges for the different transition metals. Yes, Raymond.
Can it get like 4 more electrons instead of giving away 4, like getting 4 electrons on the p orbital?
That doesn't get you to more stability, because then you still have a 5d and a 5f orbital. You still haven't filled the full shell.
I mean,
yet.
5s squared, 4d10s, and 5p6. Can it get to that point?
I mean, it could, but it's much easier, and you achieve greater stability in losing those electrons. So it's not impossible. I mean, you could get tin and bombard it with electrons and probably get it to do that, but it does this spontaneously. So yes, it can have. So 'cause basically, when we're talking about energy in chemistry, you can basically get any thing to happen under the right conditions, but it's extremely hard. What happens actually is elements bond with other elements and form something more stable. You don't get elements bonding with other elements to form something less stable. Under certain circumstances, you could force that to happen, but that's not going to happen. So it's more stable to lose electrons than it is to gain them.
Okay.
Yeah.
So you mentioned in copper, in this instance, can the S subshell give 1 electron to the P subshell and lose?
No, usually to the D. Usually you're filling a D, or sometimes a P, but usually a D orbital is being filled when you do that. Not always, but yeah, because remember, P and D and then F orbitals are very high energy. If you can fill those, you get a big bonus in more stability. Okay. Let's look at some examples, because I really want to get to something before we go, because it'll be part of the recitation this afternoon. All right, let's do a couple questions. So we're going to look at these ions forming. So we've got iodine, potassium, and indium. So we want to figure out what kind of ions they're going to form. So we write a condensed electron configuration. And remember, the condensed electron configuration means noble gas, nearest noble gas, plus whatever electrons it takes to get to this particular element. And then we figure out how they're going to achieve stability. What electrons are they going to lose, or what electrons they're going to gain. So let's look at iodine first. So I included the periodic table here because it makes our lives much easier. Excuse me, it shows us where the noble gases are, and then we can just count. We can just use the periodic table to figure out what ions, what elements, or what electrons we need to add. So where's iodine? Someone find iodine for me. Where would it be?
The
Right bottom corner.
Yeah, right there. Whoops, go back. So there's iodine. I'll just fill it in. So it has 53 electrons. So what's the next smallest noble gas?
krypton.
Krypton. So we'll put krypton. And then we just go from krypton, we go over to 37, that's rubidium, and we just add electrons. So that's the fifth period. So that's 5, and this is the S block, right? 5s2. And then we have, what's this block here? As we go from 39 to 48, what block is that?
4D.
That's D, right? That's the D block. So that's 4. 4D10. And then we come to the S block. And there's 1, 2, 3, 4, 5. 5, or sorry, P, duh.
P.
5P, 5. So when it adds an electron, or is it going to add an electron or lose an electron?
Add
Yeah, it's going to add one, right? Where's it going to go?
5p6.
Yeah. We fill the 5p level when we add an electron. So plus an electron, we get 5p6. So that's how we get, and that will give us iodine ion, or iodide, okay? Iodide, it's always fun to say. So I'm gonna let you guys see if we got that one. So it gains 1 electron, and then it looks like xenon, and everybody's happy. So here's potassium. Potassium. So someone find potassium for me. Where's potassium going to be?
$19.
19. So where? Well, yeah, I can see that. It's got 19. Where's it on the periodic table? What group is it going to be in? Or what group and what period is it going to be in?
$4S.
Yeah, it's right here. Exactly. So what is the smallest, or what's the sort of, I can't figure out a way to say it. What is the noble gas that is slightly smaller than potassium? Yeah, Raymond, don't whisper. So what noble gas are we looking at that's slightly smaller than potassium?
Argon.
Mm-hmm, argon. And so argon is here. So what would be the electron configuration of potassium, the condensed, or the noble gas configuration, the condensed electron configuration for potassium?
Argon 4s1.
There you go. Yeah, just start with argon, and it has 18 electrons. And then it has 4, and it's in the s block, and it's in the first place, so it's 4s1. And I really want you to use this method to figure out electron configuration, because it's much easier than like, when I showed you the diagrams with the lines. You draw the lines at a 45-degree angle and everything else. I find when I look at the periodic table, it helps me a lot more than looking at that, because then I can just sort of just follow it across, and then I know that I'm right, because I went across the P block and I went across the D block, and it helps me do that. So what kind of ion is potassium going to form in order to achieve nirvana?
It loses an electron, right?
What do you think? It
Great.
wants to get to a noble gas configuration. What's the easiest way for it to get there?
Yeah, to lose the electron.
Yeah, dump this one, right? Just dump it. And so what it does is it becomes potassium ion, and now has this noble gas configuration, and it loses an electron. And so that is what it does. It loses that electron. It gets rid of it. So just double check and make sure. Yeah, argon. It's isoelectronic with argon, meaning it has the same number of electrons as argon. And if it has the same number of electrons, they're going to be in the same configuration. Ferris, what can we do for you?
How come if you're losing an electron, you still put the plus electron? Do we never do like that?
That is the reaction. So that's an actual chemical reaction I'm drawing out. So potassium makes potassium ion plus an electron. That's an actual chemical reaction. So that's the way I'm drawing it. And when you're going the other way, chlorine plus 2 electrons. 2 electrons plus chlorine give me 2 chloride ions. So it's a reaction. That's what I'm drawing out. So you don't say you lose electrons. You don't have negative electrons. So you're either adding them. They're either products or reactants, basically. If they're products, that means you've lost it. It's gone now. You've given it to someone else, and you've become positive. Or it's a reactant, and you're gaining it, and so then you become an anion. Okay? Good question. Yeah, because sometimes I will do these things, and I thought, well, they must understand that I'm doing it. No, they don't understand, moron. You're being stupid. Sorry, I'm being stupid doing that. So let's look at indium, element we don't really talk much about because no one knows much about it. That's not true. Someone must know something about it. So indium is 49 electrons. So where would I find indium?
Right bottom.
So here. So there's indium. So what is the noble gas that's smaller than indium?
Krypton.
Mm-hmm. Yep. Krypton. So we'll start there. So indium looks like krypton. And then let's start adding electrons. So let's go. What's the next set of electrons I add?
5s squared.
5s2. What's the next set?
4d10.
Yep. Excellent. So here's our D block. There's 10. So 4d10. And then, am I done?
5p1.
Right. There's has one more electron. So 5p1. So, what kind of ion is indium going to be? Is indium a metal or a non-metal?
Metal.
Yeah, Raymond, just let others, just let some folks in on the game. Is indium a metal or a non-metal? I'm just going to start calling on random people if I don't start getting some answers. Ferris, what indium, metal or non-metal? I know you're out there.
Can I try?
Sure.
It's a metalloid, right? Because it's in that kind of weird in-between area.
The weird in-between area is here. So it actually isn't a metalloid. Metalloid is like silicon, arsenic, tellurium. So it's close, but it's actually still a metal. But yeah, you're really close, but it's still considered a metal. So since it's a metal, what kind of ion is it going to form? Is it going to form an anion or a cation? In order for it to achieve stability, is it going to lose electrons? Is it going to gain electrons?
A cation.
It's going to become a cation. That's right. So by losing electrons or gaining electrons?
Losing electrons.
Exactly. So which electrons, if any, is it going to lose?
There are two ways, right?
What is that?
There are two possible ways, right?
Yes, there are.
It would lose the electrons from the p.
Yeah, it could lose these. It could lose those. And then what charge would it have? You could lose that electron, and then what charge would it have?
A positive.
It's a single positive, right? So it would be indium plus. So, or indium ion. What's the other possibility? Is there another possibility? Sort of gave that away. Yes, there's another possibility. What's the other possibility?
Wouldn't it also lose 5s2?
Exactly. It could lose both. It could lose the P and the S. And so remember, that gives us remember that was called a pseudo noble gas configuration, because basically it's cleared out the entire fifth level. So the fifth level is now empty, but it does have these
So
10 here. Yes.
when you lose electrons, it doesn't matter the energy level. It just matters the. It doesn't matter the energy level. It just matters the shells, right?
Well, the shells are the energy levels, Raymond. That's what they are.
Yeah, I mean, it doesn't matter. The 5s is slightly less energy than 4D.
Yes. So if, yeah, having 4D, having that filled lowers the energy of that ion more than having a full S shell does. So you get more of an energy bonus
So
having
the
that full D
sequence
completely filled.
So the sequence of losing electrons is not as the same filling electrons, right?
Well, in both instances, you want to completely fill shells and subshells. In both instances.
Okay. Okay.
Okay. So with krypton, it has a completely filled 3D subshell. And then it's filled in the fourth level, it's filled both S and P. So it has that 8, that magic 8. But in this instance, indium would have a 4D subshell. So it doesn't look exactly like krypton, but it looks a lot like krypton, but with a full, it has the first 4 shells are filled to completion. So that's quite stable. And so when it loses both 5s2 and 5p1, what's the charge on it?
+3.
+3, right. So that would be indium brackets 3. So either of those can occur. Let's check and see if we're right on that one. Look at that, we're right again. So lose 3, and you've basically filled 1, 2, 3, and 4. You haven't quite filled 4, remember, because 4 has F in it as well. So we haven't completely filled 4, but we filled the first 3 subshells. So that's fairly stable. We haven't filled all of them. Or we can just dump the electron in the p because it has, oh, damn it. Or we can just dump the electron in the p orbital, and then we'll have then we have full subshells, S and D. So basically, you want to either fill subshells or fill shells as much as you possibly can to achieve stability. So before we finish up, I just want to go over magnetism. I said we get to magnetism, and here we are. So this is where spin comes into play, because we sort of talked about why is spin important. Oh, and someone asked me about why are all spins as you add electrons in the same direction. I forget who asked that question. It's a really good question. Anyway, why do we add them one at a time in the same direction? It's because when they spin in the same direction, there's something called precession. Basically means they move in the same way. So when they're spinning in one direction, that means they spin around the nucleus in one direction. When they're spinning in opposite directions, it means they're also orbiting in opposite directions, and they're more likely come into contact with each other, come close to each other and repel each other. So it's more stable if they're all spinning in the same direction. Until then we start pairing them up. So that's why I looked that up, and it's like, oh, that's cool, that makes sense. So thanks for asking that, because I hadn't really thought about that before. So here's where spin becomes important for a particular property. And this property is whether or not they're magnetic. And so we say that something is magnetic, we say it's paramagnetic, meaning it sort of lines up with a magnetic field. It pairs with it. So we say it's paramagnetic. And so it has to have one or more unpaired electrons spinning by itself, processing around the nucleus by itself. So this is silver. And we can see this sort of silver has kicked out an electron from 5s in order to fill the D subshell. So now it has one electron that is spinning by itself. And so it's weakly magnetic. It's slightly magnetic because it only has one electron spinning in that direction. If all of its electrons are paired up, it's not attracted at all. And we say it's diamagnetic. In fact, it's slightly repelled from a magnetic field. You try and take something that's if you have a magnet and you have something that's diamagnetic, instead of being attracted to it, it's actually slightly repelled from it. So it's not magnetic. So we need to look at the outermost shell and see which electrons are paired and which ones aren't. So let's have a look at one. I got 3 of them here, but I sort of want to get to the next thing. So let's do one, and then we'll see whether or not it's magnetic. So let's look at cobalt-3. So cobalt-3 has 27 electrons. So let's look at cobalt has 27. So how many electrons would cobalt-3 have? Cobalt itself is 23. How many electrons would cobalt-3 ion have? Oh man, everyone's tuning
24.
out already. How many?
24.
24, yeah. Because it's, so let's look at this. This is the reaction. Cobalt goes to cobalt 3 plus 3 electrons. So it's lost those 3 electrons. So it started with 27 and now it has 24. So we had all the, so just like a normal chemical reaction that we've sort of been balancing so far, for these we balance the electrons. So I got 27 electrons on the reactant side, and I got 27 electrons on the product side. So that's how we need to balance our charge. So when we're doing reduction oxidation reactions, we need to balance the atoms and we need to balance the charge as well. So here's cobalt, it's right here. There's, oops, let me go back. So here's our good friend cobalt. But it's 27, now 24 electrons. So what's the noble gas next to, the smaller noble gas next to cobalt? The next smallest noble gas. I guess that's the way to put it.
Argon.
Argon. Yeah. So cobalt plus 3, we start with argon. And then what's our next electrons to add? So I start here with argon, and then I go across to here. Then I just start adding electrons one at a time. So what are my next electrons to add?
4s2.
Exactly, 4s2. Then what?
CD4. Sorry.
Yeah, we're into D. So this is the D block, P block. So now we're in the D block and we're adding 4 more electrons, right? We're not adding 7 because we've lost 3 electrons. So we only need to add 1, 2, 3, 4. So 3D4. So if I was to draw the D orbital, how many orbitals are there in a D subshell?
5.
5, right. So I'm going to add them. 1, 2, 3, 4, 5. So put in the electrons for me. Where do they go? This is my 3D. And I got 4 electrons to put in it. So how do I put them in?
1 in each box except the last one.
Exactly. Pointing in which direction?
Up.
Up. 1, 2, 3, 4. So will cobalt-3 ion be diamagnetic, meaning it's not magnetic, or paramagnetic, meaning it is magnetic?
Pair.
It's going to be paramagnetic. It's going to be magnetic because it has 1, 2, 3, 4 electrons all pointing in the same direction that are unpaired. So it's actually going to be pretty magnetic, actually. If you put a magnetic field in a solution of cobalt ions plus 3, all the cobalt ions would move toward the magnet. So yeah, it is magnetic. So let's see what the other ones would be. So look, and we see that chromium has 3d6. Did I get that wrong? Oh, duh. Yes, I did get that wrong. No, I didn't. That's wrong. So chromium has three in the D. So those 3 are unpaired. So that's paramagnetic. And if we look at mercury +2, you can see that its S is filled, F is filled, and the D is also filled. So all of its subshells are filled. So you don't have any unpaired electrons. And so that is not magnetic. We say it's diamagnetic. And I need to double check on something. Okay. All right. So that is basically the last bit of chapter 3. Yay! So I want to sort of start chapter 4. I'm just going to sort of just hurry to a bit, and then I'm going to come back. So don't worry. I want to get to Lewis structures rather quickly, but I promise I will come back to it because I want to get to Lewis structures so we can do that recitation today. Yes.
Did we just say that do it wrong with like we did argon 4s2 3d4?
Yeah, I need to.
Did
Yeah,
you-
I think there's a problem with that. I need to double check on that.
Oh, we should.
Because cobalt 3+ doesn't have 27 electrons; it has 24.
Oh, we should lose.
Cobalt itself has 27 electrons. Cobalt +3 has 24. Same with chromium. Chromium has 24 electrons, but chromium +3 has 21. So I think whoever borrowed this slide from somebody, and I don't think they got it right.
I think we should lose 4s electrons instead of having them in the when we did it. We when we set the configuration of cobalt 3, we did we set 4s2 3d4 instead of 3d6.
Oh, I see what you mean. Yes. Okay.
Yeah.
So, but anyway, yeah, these numbers are wrong. The total number of electrons is wrong. So I need to fix that. Okay. So chemical bonding, finally. Basically, what we're going to be talking about different kinds of bonding. There's ionic bonding. There's covalent bonding. There's metallic bonding, which you're not really going to get into much. This is just basically why metals stick together. Usually what we're going to be talking about here are bonding between nonmetals and bonding between metals and nonmetals. So the comparisons between them, and we've been talking a lot about them. Yes, Nicholas.
Does this chapter correlate with the book? So this is going to be the book's chapter 4?
Mm-hmm.
Okay, cool. Thank you.
Yep. From now on, we don't need to worry. I'm working on the with the right book.
Okay,
So,
thank you.
Yeah. So we've been spending a lot of time with metals and nonmetals trying to figure them out. And so basically this sort of sums it up down here at the bottom, where when we look at atomic sizes, metals are generally larger because right as we go across, they get smaller. So we see that nonmetals who become cations or become anions are small, and the metals are generally larger. So the ZF, remember that's the amount of pull that the nucleus has, is small over here and then large over here. So that's basically why the elements are smaller, because that pull of the nucleus becomes more effective. It pulls the electrons in closer. As far as ionization energy goes, much easier to ionize metal atoms than non-metal atoms. Much easier to take an electron from them because they like to form cations. nonmetals like to form anions. And it also shows up in the electron affinity that we just looked at. The nonmetals gain a lot more stability when you add an electron to them. And so they're more negative energy because they lose more energy and become more stable when you add an electron than metals do. Some metals will gain a slight bit of stability when you add an electron, but they'll gain a lot more if they lose it. So that's why they tend to lose electrons and become positively charged. So as I mentioned, there are three types of chemical bonding that we sort of generally talk about. There's other types that are in a more advanced classes, like there's coordination bonding. There's other types of bonding, but these are the sort of basic ones that we see most, that we talk about most often. If you want to learn about other ones, a more advanced class in like inorganic chemistry will introduce you to a whole bunch of other sort of interactions. But these are the big three, shall we say. So ionic bonding, I'm probably familiar with that because we've sort of been talking about it a little bit. When we have a nonmetal and a metal. So here's our nonmetal charged and our metal charged, and they form a compound by coming together. Basically, this positive charge is attracted to this negative charge, and that's what keeps it together. That's basically all an ionic bond is two charges attracted to each other. That's it. That's what keeps the bond together. So the metal, calcium, actually loses 2 electrons and transfers them to the oxygen. So you get a positive charge created and a negative charge created. Now, covalent bonding is different in that the electrons are shared between atoms. Usually 2 nonmetals, but you can also find it with certain metals and certain nonmetals. We'll talk about some of those types of bonds. So they share electrons. So you don't see charges appearing. So that would be something like water, where each one of those lines is a pair of electrons being shared. So there's 2 electrons being shared between this hydrogen and that oxygen. And there's another pair of electrons being shared between that hydrogen and the oxygen. So then the hydrogen can say it has 2 electrons, even though it only has 1, and it's sharing 1 with oxygen for a total of 2. So it could say, well, it has 2 electrons really, and so it looks like helium. And oxygen gets 2 more electrons that it's sharing. So instead of having 6, it has 8. And so it can say, well, now I look like neon. So they're both now more stable. And then metallic bonding involves basically a whole pool of electrons. So you have what we call basically like the sea of electrons, where you have all these positive ions together, like iron atoms all together, and then there's sort of electrons swirling around between them. So at any one time, it's not charged, but then those electrons quickly move around. And that's why they're such good conductors of electricity, because they constantly have electrons zipping around the whole block of metal ions together. And so if I add more electrons on one side, they immediately can move to the other side very, very quickly. And that's why they're such good conductors. Why isn't this clearing? There we go. So here are basic models. The ionic, we get a transfer, like I mentioned. We have 2 things that are not charged, and they come together, and then one thing now is a positive charge, and one thing has a negative charge, and then they are held together by those charges. Now that's different from covalent bonding, where they start without a charge and they end without a charge. So there's no charges are transferred from one atom to another. They become stable molecules held together by those electrons that they're sharing. And then finally, metallic, as I mentioned, they sort of have this, what we call an electron sea, because they basically, it's like a commune, man. They all share their electrons. So they sort of stack together, just in a lot like the ionic mixture, ionic compounds look like, where they sort of all have a regular repeating pattern, like a crystalline pattern. Same with metals. They have this sort of regular pattern where the nuclei all sort of sit together, and then they share this pool of electrons swimming back and forth very, very quickly. They're outermost electrons, they're covalent electrons. So we mentioned the trends in electron affinity already. So we see the cations, low affinity, anions have a high affinity. And we looked at those affinities, and we saw that they get greater as we go across the table. But now I want to introduce a new concept called electronegativity. So this is a new word we're sort of being introduced to. Now that's the ability of an atom, when it's bonded to another atom, to attract that shared pair of electrons towards it. So basically it means like, let's look at water again. I love talking about water. So oxygen is more electronegative than hydrogen. So this pair of electrons right here, so I've got a pair here and a pair there. They are actually pulled more closely to oxygen than they are to the hydrogen, because oxygen, remember, pulls on, because it's a non-metal, and hydrogen's sort of like a metallic-y, it's metallic in nature. Oxygen pulls on the electrons more. There's a higher ZF. As we go across the periodic table, the nucleus pulls on those electrons more and more and more. And so this pair of electrons actually spends more of its time closer to the oxygen than it does the hydrogen. And so we say that it has a partial charge, not a full charge, but a partial charge. And this symbol delta means partial. So we say that oxygen has a partial negative charge and hydrogen has a partial positive charge. Not a full charge, it's not an ion, but those electrons spend a lot more time with new daddy than with old daddy. So they spend more time with the oxygen than they do with the nitrogen. Now, the most electronegative element is fluorine. Fluorine pulls on electrons more than any other element. So any compound that fluorine's in, it's holding those shared electrons really, really close to it. So in general, electronegativity goes down as the size gets bigger. And that makes sense, right? Because as the electron cloud gets bigger and bigger and bigger, the nucleus has a harder and harder time pulling on those electrons. Fluorine is really small. Fluorine's a really small atom, so it can pull on those electrons really, really tightly. When we move down the periodic table and start adding more shells, like iodine, for instance, is much bigger than fluorine. So it is not as electronegative because it's a lot bigger. It can't pull on electrons as much as fluorine can. So nonmetals tend to be a lot more electronegative. Nonmetals pull on electrons. They're greedy. They pull on electrons a lot more than metals do. Metals don't pull on electrons as much because they're bigger, and they tend to give electrons away. And how we measure this, basically, it's a concept that Linus Pauling came up with. You may have heard of Linus Pauling, famous chemist. Actually won 2 Nobel Prizes, one for chemistry, for basically describing the electron bond, the covalent bond, and he won for a Peace Prize. And he was very big into vitamin C. You may have read, he used to just eat just unbearably large amounts of vitamin C. He was determined that it was going to make him live forever. He was right about a lot of things, not right about everything. But this was his scale, and he came up with this scale on his own. And for some reason, why it's not 0 to 10, I don't know. He made it from 0 to 4. Why 4? I don't know what it is. But anyway, fluorine is the highest. So fluorine is the most electronegative element there is. It doesn't matter who fluorine's bonded to, it's taking those electrons, or it's keeping them closer to fluorine than the other element. Cesium has the lowest. So we can see that the bigger you get, the harder it is to pull on those electrons. The smaller you get, the higher your electronegativity goes. And the more non-metallic you get, the higher your negativity goes. So you don't have to memorize this, but one thing that will show up over and over and over again are these 4 elements here: nitrogen, oxygen, fluorine, chlorine. They're the top 4. They're the 4 most electronegative elements, and they show up a lot, especially oxygen and nitrogen. They show up all the time. So they're super electronegative. And then you can see over here, the metals, very, very low. So why are we introducing this? Because it's the difference in electronegativity that leads to the type of bond we're going to talk about. So an ionic bond forms when the difference in electronegativity is so large that basically that electron just moves. Instead of being shared, it just moves from one atom to the other. So there's a big difference in electronegativity. So instead of sharing, it's not going to bother sharing at all. I'm just going to take that electron. That's what fluorine does. Fluorine basically takes an electron from pretty much everybody, with the exception of nitrogen, oxygen, chlorine, the other halogens. But it'll basically just steal an electron from everybody else. So an example here is lithium and fluoride ion, lithium ion, fluoride ion. So we start with lithium. So it has that 2s1 that it loses. So this electron will go over to fluorine because fluorine has 2p5. And fluorine pulls on electrons more than anybody else. So this electron will physically move from lithium to fluorine. And now lithium looks like helium, and fluorine looks like neon. And so they're both very, very stable, and they're now charged. And this is where I didn't quite time that as well as I hoped. This is where we talk about the electron dot, or the Lewis dot structures. Now we add a dot for every atom
Valence.
in the outermost shell, the one that's going to be shared. So lithium has 1 in its outermost shell, and fluorine has 7 in its outermost shell. And so we put a dot around each one, representing each one. And the way we add the dots is in pairs, because as we see, electrons are going to be in pairs. And so if we have fluorine, we go 1, 2, 3, 4, 5, 6, 7. We can see that fluorine is going to have 3 sets of paired electrons, and it does 1, 2, 3, and it's going to have 1 unpaired electron, this one. And so when it's an ionic bond, it's just going to steal that electron and keep it. And when it's covalent, it's going to share it. So in other words, if we have hydrogen with its 1 electron and fluorine with its 1, 2, 3, 4, 5, 6, 7, this will pair with that, and we just give it a line to represent the shared pair of electrons. Now we'll do a lot more of this afternoon. I'm sorry we didn't get to talk about it more in depth. We'll talk about it in recitation, and we'll talk about it in class on Tuesday, okay? But yeah, I really wanted to, so we're gonna learn about how to represent bonds, because as we learn to represent bonds, we'll figure out how that moves into shapes of molecules. So we did a lot today. Any questions?
So uh, if two elements have the same electrode negativity,
Mm-hmm.
would the electron go either way or just
Still be shared
Uh,
completely. We call that a nonpolar covalent bond. Yeah, and we're
Okay.
going to talk about that next class, because there's two kinds of covalent bonds: polar, where the electrons are not shared equally and spend more time with one element than the other, like with water, where you have partial charges, where the oxygen is slightly negative, not negative enough to be a full negative charge, but more negative, and the hydrogen is slightly positive because the electrons are further away from the hydrogen and closer to the oxygen. So it's not enough to be a full positive charge, but it's slightly positive. That's a polar bond. Now, a nonpolar bond would be where the difference is very, very small. And so there's sort of equal distribution of electrons all the way around. Yeah, we're going to get to that next class. That's a really important part of this chapter. Right. Any other questions before we go?
What are metallic properties again?
Oh, the metallic properties are they're shiny, and they tend to lose electrons. They tend to lose electrons and form cations. They tend to be malleable. The reason why they're malleable is because they have that sort of that sea of electrons sort of swirling around, so you can bend them, and it doesn't really change the distribution of electrons, because they're sort of free flowing, and so you can bend them, you can flatten them, and they tend to conduct electricity really, really well because they have all those valence electrons just floating around, moving freely about. So if you add a charge on one side, the electrons will easily move in one direction toward the positive charge. So those are the basic metallic properties.
The recitation isn't on Canvas, right? Not yet?
No, it will be as soon as I'm going to post it as soon as we finish class.
Okay, thanks.
Yeah. Anything else before we go? Okay. So yeah, my group will be meeting, my groups will be meeting this afternoon, and AJ's group will be meeting this afternoon as well. I think you're not going to be working on this recitation yet. You'll be working on it next week, but we are going to be having a discussion with AJ about something fascinating. So I will see my groups this afternoon. Chill out. Everyone will get their marks by next week, and then we will continue with our happy lives. Okay?
Okay.
I'll talk to you soon.